Otherwise, it is too expensive. And the maximum is 3 kilowatt. So from 1 kilowatt to 3 kilowatt. And this is the best converter because it uses 4 switch, 1 transformer, 4 die, 1 inductor, 1 capacitor, and a load. So can you use the transformer to the same transformer as Taiwan Power Company? So you just use traditional transformer. What is traditional transformer? It looks like this one. You call it is traditional, right? Use steel. So can you use traditional transformer? The answer is no, because the switching frequency is 120 kHz, not 16 Hz. If you use traditional transformer, then the loss, the core loss become too huge because your frequency push too high. So you cannot use traditional transformer. What kind of transformer can you use? You have to use what we call high frequency transformer, or you can call it is Ferrite. Ferrite transformer. What is Ferrite transformer? It could be like this. So you have to make this kind of transformer, right? We call it is Ferrite, high frequency transformer. Then you can design this one for what? For electrical motorcycle charger, right? So if you drive electrical motorcycle, they say you need $3,000 to buy a charger. You say it is okay. If you want to buy a cell phone charger, they say $3,000. You say it is not okay, right? So this is a high performance. We call DC-DC converter. So what is the principle? So you can turn on the Q1 and the Q2, and then turn on Q2 and the Q3, right? Q1 and the Q4, 50%. Q2 and the Q3, also 50%. Then you can get the waveform like this. So this is Q1, Q2, this is Q3, Q4, then the output is like this. So output is like this. So it is V1 minus V2. So V1 minus V2, here is VDC minus 0. This is VDC. VDC minus VDC becomes 0. 0 minus VDC minus VDC, right? So in the primary side, you can get this voltage. And then you have turn ratio, maybe reduced to 10% because you have 10 by 1 transformer ratio. And then your output is equal to the duty cycle multiplied by the secondary voltage, right? So you can get this voltage. So your output voltage is related to what? Anybody has any idea? Is proportional to what? So from here to here, how can you get a VG? VG is the time, the phase angle between V1 and V2, right? So what is the output voltage? It is related to the what? Phase delay, phase angle, okay? If you delay more, then output become more. So you can see the relationship. This is the delay between V1 and V2. So if your delay angle is 90 degrees, then you can get very large output. If your delay angle is 0, then this minus 0 output is always 0, right? So your output is related to the phase angle. So this is like this. This is phase angle. This is your output. So output is related to the phase angle. If your phase angle is negative, output is negative. If your phase angle is positive, output is positive. If your phase angle is 0, output is 0. So you can see the output is related to what? Phase delay or phase angle. So you can control the phase angle to control the output. How about your duty cycle? What is this duty cycle? 50%, right? What is this duty cycle? 50%. So duty cycle always 50%, but you control the phase to control the output. So the principle is very clear. So we can adjust the phase angle, then we can control the output voltage. And we have isolation between the input and the output, which means your motorcycle side only low voltage, maybe 20 volt. So you never damage your battery. So this is the good point. You can protect your load. So it is similar to a buck converter because you only can reduce the voltage, right? You cannot make the output larger than the input. So it is a buck converter. So we call it is a full bridge DC-DC isolated converter. So this is the best one. So we skip this. So how about your boss say it is too expensive? Can you develop a cheaper charger, right? A cheaper charger. Then you go back to propose this one. If you propose this one, how many devices do you need? 1. Before, how many? 4, right? How many transformer do you need? 1. How many diode do you need? 1. Before it's what? 4. And then no inductive and the output. So you only need 1 switch, 1 transformer, 1 diode, 1 capacitor. So your cost become 25%, right? So you can propose this idea. So if you turn on the switch, then what happens? Your voltage Vs across the YD. So you have Vs YD. If you turn on the switch, then plus minus, then this is plus minus, then diode is part off, right? So if you turn on the switch, then diode is off. If you turn off the switch, then the voltage is minus, plus. This becomes minus, plus, then diode turn on. So if switch turn on, diode turn off. If switch turn off, diode turn on, right? So if the diode turn on, then we can get output. So you can see if the switch turn on, we get Vs. If switch turn off, then diode turn on. Then this is second voltage. Then how about the primary side voltage? It is N multiplied by V second. So N multiplied by V second. But it becomes negative because if diode turn on, then what happens? This is plus minus, then the dot is minus plus, the voltage is inverse, right? So you can see if you turn on the switch, Vs. If you turn off the switch, then this is VO multiplied by temperature minus NVO. And this area should be equal to this area because this is YD, right? The average voltage across our YD should be equal to what? 0. So this area equal to this area. So if you turn on the switch, then how about I1? I1 is equals because VL is equal to Vs and the VL is L di dt equal to Vs. Then how about di dt? So you can calculate di dt. So di dt is equal to Vs divided by L. Is is equal to initial value plus VSL multiplied by T. So you can see it is like this, right? So the current is increased. Then if you turn off the switch, the initial current is here. Then you go this way. So you have output voltage here. You have this become turn off, this become turn on. So your current is decreased. So you decrease your current, and until it reaches 0, then you can turn on, and then you can turn off. So you can draw the figure like this. So I have a question. If your current not reach to 0, can you turn on the switch? Yes or no? No, because this flyback converter should be guaranteed your current reach to 0, then you can turn on. It should be discontinuous, right? Discontinuous. So you can see this waveform. So this is a primary, how about secondary? Secondary, this dot here, this dot here, so voltage is negative. So this is Vs, how about this one? Vs divided by N. This is minus NVO, and then you reverse divided by N, it becomes VO. So this is the second side voltage. So we call this is what? Flyback. Flyback. So flyback become very simple. But what is the disadvantage? Discontinuous, right? The current should be discontinuous. If the current is discontinuous, how about the output voltage? Because here is 0. So we have 0 current here. Then the output voltage becomes decreased, right? And then this turn on, then output voltage increase. So because we have a huge current change, then how about output voltage? It changes very huge. So output ripple is very huge. So this is the disadvantage. We have huge output ripple. If you have a charger, do you like huge output ripple? No, because it will kill your battery, right? So this is not good, but this is cheap. Okay, so we can develop flyback converter. So what is flyback converter? When you turn off, you have a voltage space. The voltage space is Vs plus NVO. So it almost double, become 2Vs. So which means if you turn off, what across the switch? 2Vs. If Vs is 100 volt, what is 2Vs? 200 volt. So your voltage space become 200 volt. Then do you think this switch become cheaper or more expensive? Originally you use 100 volt, but now you have to buy 200 volt voltage switch. Then do you think the switch become cheaper or more expensive? More expensive. Because your voltage switch is higher. So if you buy a switch, the switch voltage switch is only 300 volt. But now you say I need a 3000 volt voltage switch. Then the switch become what? More expensive, right? So this is voltage switch become larger, become twice. So this is one disadvantage. And half the core excitation is used. So what does this mean? This is a transformer. But for transformer, the primary side only half cycle turn on. The second side only half cycle turn on. What is a transformer? Transformer should be AC voltage, AC current. But do you think this current is AC or DC? AC or DC? So I ask you, this current is AC or DC? DC. Can you use a transformer with DC current? No. So can you call this is a transformer? Because transformer need balance. So the positive current should be equal to negative current. But here, you only have positive current, no negative current. Then the transformer will be damaged, right? So can you call this is a transformer? No, we cannot call it is a transformer. We call it is two coupling inductance. Two coupling inductance. This is primary inductance. This is secondary inductance. We do not see this is a transformer because when this turn on, this is turned off. Then the current is 0. So when this turn on, this is turned off. Can you use a transformer like this? No. So we call it is coupling inductor, not a transformer. So this is the disadvantage. We are not use this as transformer. Half the core excitation is used. Then what happens? If you buy a 1 kilowatt transformer to this application, you only can use maybe 250 watt. Otherwise, you will damage your transformer. So if you drive a car, with 3 wheels, 1 wheel broke down, you only have 3 wheels. Can you drive to 6 kilometers per hour? Then you will have car accident. So what can you do? You say, oh, I only can drive my car 10 kilometers per hour. So we call this what? Delay. So if you are very healthy, you say, oh, I can work 10 hours a day. If you are sick, can you work 10 hours per day? No, you only can work 2 hours a day. So you have to do what? Delay, right? Delay. So we have to delay because we use this not a transformer. We use this like a coil. So we have to size penalty, which means original the transformer is high power, but I cannot use full power. I only can use 20%. So when I was healthy, I can work 10 hours a day. But today, I am sick, so I only can work 2 hours, right? So this is delay. And the ripple is so huge. If you want to reduce the ripple, what can you do? You use a high capacitor at the output. Try to filter the ripple. So the output capacitor become very, very huge. And if you design this circuit, the maximum power is 100 watt. If you large than 100 watt, it becomes worse, and then you cannot use it. So if you was sick, you tell your boss, my maximum working hour is 2 hours. If I work more than 2 hours, then I will die. Right? So you have to delay. So maximum 100 watt. If you use this technology to charge a motorcycle charger, then it just burn out. It doesn't work. So from 50 watt to 100 watt, maybe you can charge your cell phone, but not your motorcycle charger. So we call this is flyback converter. Then you say for some device, I need a better performance. more than 100 watt, I need 300 watt. Then what can I do? I have to develop a new one. Forward converter. Forward converter. So what is forward converter? It is like this. So before we only use one diode, but now how many diodes? 2 diodes, right? 2 diodes. Before here, we only use one switch, but now we add 1 diode and 1 coil, right? So if we use more device, means the performance become better. But do you think that this can compete with full bridge? No. Full bridge use 4 switch, 4 diode. But here only 2 diode and 3 diode, 1, 2, 3, and 1 switch. So the performance is between flyback and H bridge, right? So the maximum power is 300 watt. So if we turn on this one, then what happens? So the voltage Vs across the winding, so Vs. If we turn off this one, then the diode turn on. If the diode turn on, then we have plus minus. Then here we can have primary the same. So this is minus, so this is also minus. So you can see if this is Vs, what is this? Vs divided by N. If this turn off, then the diode turn on. Then this is VO. And for the primary side, it become a VO. So this area should be equal to this area. And how about the current? If we turn on, then the current increase. If we turn off, the current decrease. So we see the magnetization current. If we turn on, then the magnetization current increase. If we turn off, then the magnetization current can reduce. So then the magnetization current should be discontinuous. So we have to follow this rule. Then we can improve the performance better than flyback, but less than full bridge. So this is between the middle. If you use this one, you can use from 100 watt to 100 watt to 300 watt. So this is forward converter. So this is the detail. If we turn on the switch, then we have voltage VD. If we turn off the switch, then we can get negative voltage. And we have VO refer to primary become minus N1, N3, VO. And then we have magnetization current from here is increase, here become decrease. And this is the inductor current. So we can draw the whole picture to analyze the forward converter. And we also can design Choke converter. So what is the advantage of Choke converter? Do you remember? We can think the capacitor can be used 2 capacitor series. Then we can break here. Then we can put transformer. If you use buck push, then you have no opportunity to use transformer, right? So this is one advantage. Another advantage is if you design the Choke converter, the L1 and the L2 current always continuous. So more smooth. And we can use either buck or boost. So in this case, the transformer can never get saturation because we use capacitor here to block DC voltage. If you have DC voltage, then the capacitor will block the DC voltage. Why? Because the capacitor If frequency is 0, then what is the capacitor reactance become infinity. So when can DC flow into the capacitor? No. Capacitor is only coupled for what? AC. So you can see we can use the capacitor to remove the DC current or DC voltage. Then the transformer never get saturation. If you have DC current, transformer will get saturation. So the curve is like this. So if you have DC bias, it is easy to get saturate for your transformer, right? But now you block the DC current, so your transformer never get saturation due to the DC frequency or low frequency, because DC component is blocked by the capacitor. So this is an advantage. So you never damage your transformer because no DC current can pass to the transformer. So this is the advantage. And you say, I need something between forward and H bridge. So I need 300 volt to 1.5 kilowatt. Then what can you use? Dual forward converter. So what is dual forward converter? If you turn on this one, then you can go this way, plus, minus. If you turn off this one, then the current is go this way, then they can go this way. Then you can get this one is minus, plus. So if switch on, plus, minus. If diode on, plus, minus. Then you can use transformer to do rectify to get DC. So we call this is dual forward converter. The dual forward converter use 2 IGBT, 2 switch, 2 diode, 1 transformer, and here also 2 diode, so total 4 diode and inductor capacitor. So the device is below H bridge, but more than forward. So the performance is between forward and the dual bridge. So we have many choices. So this is a waveform. So you can have, if this turn on, then we have 0 voltage. If turn off, then we have VDS voltage. If both are turned off, then 0.5 DC voltage. So you can see the switch 1 and the switch 2, they have, we call this is increased current because positive voltage. Then 0 current, then positive voltage. So we can have the waveform like this, so the output is like this. So we call this is dual forward converter. And this is full bridge we discussed before. So we also can use the transformer with center point. If we use transformer with center point, then we can reduce 2 diode, right? We only use how many diode? 2 diode. If your transformer has no central point, you have to use full bridge rectifier. How many diode? 4 diode. So we can also design this full bridge converter. So this is a waveform. So until now, we introduced how many converter? H bridge, right? And then what? Dual forward. Then what? Forward. Then what? Flyback. Right? So now I give you one question. You say flyback is the simplest, cheapest one, right? Flyback. We call it is the cheapest one device. So flyback. I try to get the flyback. Oh, this one. So I give you one research topic. Can you find another simple circuit than fly back. I need to reduce some device. Can I do this? So we can try to reduce. This is a switch. Can we remove this switch? No switch. If your circuit is no switch, can you design a converter? Impossible, right? So can I remove this switch? No. Can I remove this transformer? Without transformer, can we isolate input and output? No, right? So transformer is required. Then this is AC. We use one diode to convert AC into DC. Can we reduce this diode? No. We cannot reduce this. We cannot reduce this. We cannot reduce this. Can I reduce the capacitor? Then your output is not smooth. Can I reduce the load? No. So what can you do? If I give you a research topic, can you design a new circuit, new converter, which is simpler than flyback converter? What can you do? If you can do it, you can get a PhD tomorrow. So can you go back to sleep and then think about it? If you can do it, you can turn it to me. I will give you 10 points. Okay? So this is optional. So the circuit is like this. So the problem is, can you design a new circuit which is simpler than this circuit? So this is, you can get 10 points. Okay? So you can think about it. So in general, we always say flyback is the simplest one. Which one is the most complicated? H-bridge. Right? So we can design the converter between flyback and the H-bridge. Okay. So we have many choices. Then, if you use this topic to do research, then you focus on circuit, right? Topology, circuit, waveform. Do you need to control your converter? Because your output voltage needs regulation, right? So if you want to control your converter, what do you need to know? Your plan, right? What is your plan? Your mathematical model of your plan, right? So what do you need to know? Model. So if you want to design an amplifier, what do you need to know? I need to know the equivalent circuit of the transistor, right? The equivalent circuit of the common base, common emitter. I need a small signal. Now you have converter. So my question is, what is the mathematical model of your converter? So you say, my converter is switch. So you have a converter. So this is your circuit. So what is your mathematical model? What is the mathematical model of switch? So if you have inductor, what is the mathematical model? LS. If you have capacitor, what is the mathematical model? CS, right? If you have a transformer, then what is your mathematical model of transformer? You have stator resistance, you have stator leakage inductance, you have secondary leakage inductance, secondary resistance, you have magnetization inductance, you have core loss. So you say this is your model, mathematical model of transformer, right? If you have DC motor, what is your model? You have resistance, you have inductance, you have back EMF. So the back EMF is KB omega. So you say this is a mathematical model, right? So everything has model. So now you do PhD, you do master degree, then your committee will ask you, what is your model of a buck converter? How can you describe the model of a buck converter? Then you ask, why do I need this? Because you need closed loop control, right? If you need closed loop control, you need to know your model. Otherwise, how can you design controller? So now I have this one. I have, for example, I have this one. So this is boost converter. I have this one. I have this one. But I need to control output voltage. So I have desired output voltage. I can feedback the output voltage. So I have error. Now I design controller here. And then I can control the switch. So I need to know how to design the controller, right? If I want to learn how to design the controller, I need to know what is the model of my circuit. So can you tell me what is your model of your circuit? You say it is a switch. What is the model of switch? You say I don't know. Then how can you design the controller? There is no way, right? There is no way. So it is a big issue if you choose the converter as your research article. Then what should you do? You have to say something about the main circuit, the topology, right? And then the waveform, and then the control. If you want to say something about control, you have to say something about the model. So what is your mathematical model of a buck converter or a boost converter? So this is challenge, because you say, I have no idea, because sometimes it's 5 volt. It is like this. Sometimes 5 volt, sometimes 0 volt. So it is a high frequency. So what is the model of high frequency? You say, I don't know. Then how can you design the controller? I don't know. I use try and error. Then how do you know you are correct? I don't know. Then what is your research? I don't know. Can you pass the oral exam? I don't know. So if you are a master degree or a PhD student, what is important? Basic concept, right? So you have to say something about your model, and you have to guarantee your control method is stable. Otherwise, it becomes unstable, right? So you have to tell me how to choose the proportional gate and the integer gate. So you have to learn something about model. So we will discuss about the model of converter. So we will include 2 parts in the future. So how can we determine a model? If you have a plate, you want to know the model of the plate. How many ways can you use? In general, 2 ways. One we call it is what? Transfer function, right? So we take u and y. We say y divided by u is transfer function. So we call this is transfer function. So we care about input and output. Only 2 things, input and output. And how about the inside? Black box. I don't know anything about input. So we take this as a black box. So we call this is transfer function. I only care input, output. Another way is we have to use state space. So we have parameter A, B, C. So we call this is what? State space representation. This is state space representation. So we have two ways. One is transfer function, another is state space representation. So which one is better? Which one do you like? State space. So if you have a motorcycle, what is your input? Your input is you can put gasoline, right? What is your output? Speed. So you know the relationship between your input and the output. If you push more gasoline, then the speed increase. If I reduce the gasoline, the speed decrease. So it is a transfer function. So you say it is okay. But one day you push the gasoline, but the output is 0. Why? Because you have no battery. So you only care about what? Gasoline and the output. How about battery? How about water? You don't care because you think I only care input and output. So do you think transfer function is a good way to describe a system? No, in general, no. If you take an airplane, do you think the pilot only care about gasoline and speed? No. You see the display, the height, the wind speed, the location from the original, the location from the destination. So how many state variables? Maybe 20 to 30. Why the airplane needs so many state variables? Because it is advanced technology, right? So if you use state space, you can get a lot of information. We call this is state variable. So the state variable include the height, the speed, the velocity, the wind speed, and the altitude. A lot of state variables. So for converter, how can you describe a converter? Two ways. One is what? Transfer function. Another is what? State space. So you only can use two ways, and we will discuss about this idea. Then we can model the DC-DC converter. Then we can control the DC-DC converter. Then we can evaluate the DC-DC converter. You can say, what is my desired response? What is my real response? What is my bandwidth? And what is the relationship between the duty cycle and the output voltage? What is the relationship between duty cycle and the output ripple? So we can develop a lot of math. So it is important. So the first one is AC equivalent circuit modeling. So we have this one. What is this one? So if we turn on this switch, then we charge the inductance. If we turn off this switch, then we have to go this one. So this is boost converter. So the circuit is boost converter. So we take the boost converter as an example. So first we charge the inductance. Next, maybe we can generate the output voltage. So now we have to discuss the input-output relationship. So what is this? This is a switch. What is this? Dial, right? So what is what? What is what? Switch, right? What is switch? this one, this is diode. So if switch on, diode should off. If switch off, diode should on, right? So we call this is 1/9 pull through. So we can pick up this one, turn on this one, then this is turn off. Or we can turn on this one, then this is turn off. So what is this switch? We can choose this one, or we can choose this one. We call it is 1/9 pull through. Pull through, right? 1/9 pull through. So we use this idea. So either this one on or this one on. Then what can you do? What can you do? If you have this circuit, my question is, what is the relationship between output and input? Can you show me if input have 1 millivolt ripple, how many ripple will create an output? So you have to find the transfer function, right? So can you do this? You say it is a challenge, right? Very hard. So we know this is challenge because it is not easy. Because our circuit is switching. Have you learned how to model a switching circuit? No. Because if I turn on here, then I have different model. If I turn on here, I change my model. So how many models do I have? 2. How can I combine 2 models into 1 model? It is very hard. So if you have a robot, the robot actuator is here, you get 1 model. If the robot is stand here, you get another model. You have 2 models. How can you control 2 models? Impossible, right? Impossible. So this is challenge. We will discuss how can we do the modeling. So it is quite complicated. So I think I will stop here, and I will see you the Monday after next week. Okay.